Welcome back, class. We're continuing in this video to talk about graph colorings. And before I go on to prove more things about graph colorings, I wanted to point out that as much as this is posed as a very theoretical question, this is actually a question that really shows up in the real world in a bunch of cases. So I'm going to show you one of the cases where this shows up in my life. So, at some point before the semester starts, everyone on campus has to decide what classes they're going to teach and at what times. And so I've just put here, for example, 6 classes, but you can imagine that really this graph includes all the classes that are going to be offered on campus, or at least all the ones that are going to be offered Monday, Wednesday, Friday. And what I've done here is I've drawn an edge between 2 classes that should not be offered at the same time. So, for example, very often an incoming physics major will start in Math 152, so they should not have these 2 classes at the same time, because then the student couldn't take both of them. Or, likewise, a second-year physics student will likely be in linear algebra, and so on. So there's all of these different connections. And again, you can imagine that there's this huge graph of all the classes on campus where there's an edge between 2 classes if it's deemed likely that a student will want to take both, because you can't be in the same place at 2 times. Sorry, you can't be in 2 places at the same time. There we go. That was the right order. Okay, so then why is this a coloring problem? Well, ultimately, when we're scheduling them, what we're doing is we're assigning one of these, quote, colors to each vertex. That is, each class gets one of these 6 colors. And the goal is we want to make sure that no 2 classes that are adjacent get the same color. That is, no 2 classes that there's an edge between, because we don't want them to be at the same time, are at the same time. And so this question, which again, we're largely treating as a theoretical interest question, of, okay, if there's a graph, what's its chromatic number, or how do I come up with a coloring, or what's the best coloring I can come up with? This is actually a very relevant question that shows up in all sorts of scheduling problems. Okay. And there are a lot of scheduling problems even beyond just campus life and scheduling courses. So you can imagine how this shows up, and the various algorithms behind it end up being very important. Okay, so let's start by offering a proposition that's going to help streamline some of our proofs that we've actually found the correct chromatic number of a variety of graphs. And so this proposition is that if H is a subgraph of G, then chi of H is less than or equal to chi of G. Okay, so let's think about this. What does it mean, again, to be a subgraph? A subgraph here means that the vertices of H are a subset of the vertices of G, and the edges of H are a subset of the edges of G. Okay, and of course, if you dropped one of the vertices out of G, then you definitely can't include any of the edges that included that vertex. So, what's the proof here? Well, the proof is basically obvious. It's, hey, if I can color G in, say, n colors, well, do that, and then just throw away all the vertices and edges that are in G but aren't in H, and then what you're left with still meets all the requirements of a coloring. Okay. So if you can color a graph on 100 vertices in 6 colors, and then you throw away 50 of those vertices and all the edges, that were connected to those 50 vertices, well, the remaining graph can still be colored in 6 colors. That's all this is saying. And so what this means is if we can identify a subgraph of a graph whose chromatic number we know, that gives us a lower bound of the chromatic number of the bigger graph. So let's start with the Peterson graph. We have not yet talked about the chromatic number of the Peterson graph. And so I claim that the Peterson graph, which remember is this thing with a star in the middle, like that, I claim that chi of the Peterson graph is 3, that this is a 3-colorable graph, but it's not 2-colorable. Okay. And so remember, this includes 2 pieces. Piece 1 is it can be colored in 3 colors. Okay, well, if you want, you can play your own little game and figure that out for yourself, or you can look at this picture that I've just popped up on the screen and see, aha, there it is in red, blue, and green. Okay. Also, I need to prove that P cannot be colored in 2 colors. Okay. But here's where I'm going to use this whole idea about a subgraph, because I see that if I take just these 5 vertices and just the edges between those, that's a C5. Right? And we've previously on this show, last episode, we showed that if you take the chromatic number of the cyclic graph on 5 vertices, that is 3. Okay. And so why can P not be colored in 2 colors? Well, it can't be colored in 2 colors because it has a subgraph isomorphic to C5. Okay, so since C5 is a subgraph of P, chi of P is at least 3. Okay. In fact, if you really want to think about it this way, when I say that P can be colored in 3 colors, what have I really proven? I've really proven that the chromatic number of P is at most 3. Right? If something can be colored in n colors, that puts an upper bound on the chromatic number of the graph. Whereas if it has a subgraph whose chromatic number you know, that puts a lower bound. And in this case, the upper bound and the lower bound, they happen to be equal. And so we're in good shape. Okay, so that proves that the chromatic number of the Peterson graph is really 3. Okay, let's do another example of this. So let's imagine here that I'm going to take a chessboard, and I'm only going to draw a 3x3 chessboard, but you can imagine here that we're really on an 8x8 chessboard. And I'm going to draw here a vertex in each square. And I'm going to connect those vertices if the squares are adjacent. So these connect, and so on. But I'm also going to connect the diagonally adjacent ones. So there and there, there and there, there and there. Okay. So if you want to phrase this in chess terminology, what I've really said is that 2 squares are connected by an edge if a king can move between them. And so if I call this the chessboard graph, which I'll abbreviate CB for chessboard graph, or CB8 for the 8x8 chessboard graph, then my question is, what is chi of CB8? Okay, so I need again to sort of figure out what's the fewest colors that I can use. And so I look at this, and maybe my first inclination is to say, okay, well, I'm going to start with the regular checkerboard coloring. And so I'll go across here, and I'll go, okay, so this will be blue, and then that'll be red, and this will be blue, that'll be red. And I'll just alternate across the top, just like that. So blue, red, blue, red, blue, red. Now, in a normal chessboard, we would now alternate these colors again, except this tile here, it can be neither blue nor red. It has to be something else. So I'll go ahead and I'll pick yellow. And let's try the same thing. Now, this square, it can't be any of those colors. It can't be blue or red or yellow, but it could be green. And now this one can be yellow, and so I can go so on and so forth across there. And now for this next row is completely disconnected from the blue and the red, so I can actually repeat the blue-red piece that I did before. I go blue, blue, red. Okay, and so what I've sort of demonstrated here in the case of the 3x3 chessboard, and which I think you can convince yourself of in the 8x8 version, is that I can color this in 4 colors by alternating blue and red on the top line and alternating yellow and green on the second line, and then every other line switching between the 2 colors. Okay, so what does that mean? That means the chromatic number of CB8 is less than or equal to 4, because I've given you a 4 coloring of the graph. Okay, now, how do I know the chromatic number isn't 3? Well, that means I need to find a subgraph of this graph whose chromatic number I know is 4. And if you just think briefly through what are the graphs whose chromatic number I know is 4, the graph whose chromatic number we know is 4 is the complete graph on 4 vertices. And so can I find a subgraph here that's the complete graph on 4 vertices? Well, sure. If I take just these 4, that is a complete graph on those 4 vertices. Okay, and so CB8 has K4 as a subgraph. Okay. And all that really means is these 4 vertices, the upper left 4, those are connected in all possible ways. And thus, this is a complete graph on 4 vertices. And we've already observed that the chromatic number of the complete graph on n vertices is definitely n. 4 is exactly 4. So that tells me that chi of CB8, that's at least as big as 4. And since this number now is at least as big as 4 and less than or equal to 4, we get that the chromatic number of this graph actually is 4. Okay. So that gives you some idea, and that can streamline proofs and let you bootstrap from lower examples that you know are simpler examples to more complicated ones if you look at the problem in the correct way. Okay, next up, let me remark on another way that we can get a bound on the chromatic number. Okay, and so far our bound on the chromatic number is a lower bound. Let me tell you how to get a bound on an upper bound on the chromatic number. Okay, namely, I'm going to let delta here be the maximum degree of a vertex in the graph. Then the chromatic number of G, it's no bigger than delta plus 1. Okay, so if you find a vertex of degree 5, but no vertex of degree higher than 5, then you know your graph is automatically 6 colorable, for example. And the proof here is to give an algorithm that produces a delta plus 1 coloring. Okay, so here's step 1. Choose an uncolored vertex. Step 2. So I'm going to be looping through this algorithm, so I'm assuming my graph is partially colored at this point, but some vertices aren't colored yet. So I choose an uncolored vertex, and I can do that at random if you want, or in some systematic way, whatever. Just choose one of the uncolored vertices. And then I'm going to color that vertex in a color that it's not adjacent to. Okay, so now here's where, in order to claim that this is really an algorithm, I have to make sure I check that this algorithm can't get stuck, that I can't be asked to do something that I'm not allowed to do. Okay. But remember, the maximum degree of the vertex, or of a vertex, is delta. So at worst, this vertex that we've chosen is adjacent to delta other vertices that are all colored in delta different colors. Okay. However, we have delta plus 1 colors to choose from. Okay. And so this is really a pigeonhole principle application. I have a box for each color of an adjacent vertex, and if I throw all of those vertices, all of those delta vertices into the box corresponding to their color, I can't possibly fill every box because I only have delta vertices and I have delta plus 1 boxes. So by the pigeonhole principle, I can always choose a color that's not adjacent, or not the same as the color of an adjacent vertex. So this is possible by the pigeonhole principle. Notice, once you have this, this plus 1 here really came exactly from the pigeonhole principle. Namely, I have delta as the maximum degree. I really need delta plus 1 as my number of colors here in order to use this sort of algorithm. Okay, and then step 3 is just go back to step 1, unless you're done. Okay, if you are done, well, then you're done. Okay. But in this fashion, one at a time, we color every vertex in the graph, and we do it in a way that does not break the rule that you're not allowed to color adjacent vertices the same color. Okay. So this is an algorithm, and this is actually a pretty good algorithm to use to try and come up with a reasonable coloring of a graph. And indeed, if you proceed in a way that is slightly less random, you might end up doing better than the algorithm suggests you will. So let's take this graph. I'll go ahead and put that there, and I'll go ahead and connect that one over to here. Okay, so here's a graph where the maximum degree of a vertex is 4. So my algorithm told me that this graph I can definitely color in 5 or fewer colors. Now the question is, do I really need 5 colors? And so let's try and think about this. If I'm going to do this and I want this algorithm to be as successful as possible, which vertex should I start at? Well, the most constrained vertices are the ones of highest degree. So what makes sense is to start at the highest degree vertex. So in this case, the highest degree vertex is this one. So I'm going to color that one blue. Now, next up, I want to look for, oh, hey, here's another highest degree vertex. That one also has degree 4. So I will color that one red. Next up, I want to look for the next highest degree vertices. And so, in fact, that vertex, in fact, every vertex now has degree 3. So I just want to color each of these with a color that I haven't used yet. Okay, so for example, this vertex is adjacent to the green and the red vertices. So I need to use, this vertex is adjacent to the blue and the red vertex. So I need to use a different color for it. Let's use green. Okay. Now let's just keep going. So this one's adjacent to the green and the blue, but there's no reason I can't use red for this vertex. So I'll use red. Okay, now this vertex, I could actually use blue or green. Let's go ahead and let's use blue. And now this vertex up here, it's connected to a blue and a red, so I can use green. Okay, now notice the theorem only guaranteed me that I would be able to use 5 colors. Okay, so theorem. But what we actually did was to use 3. Now, note that the theorem didn't say anything about this is the number we need. It just said you could use this. We did better. Okay, so if this is the graph G, we showed that chi of G is less than or equal to 3. On the other hand, in fact, you can see this C5 on the outside, the cyclic graph on 5 vertices, which has chromatic number 3. Okay, and so since this graph has a C5 subgraph, chi of G is at least as big as 3, and so putting those two facts together, we get that, in fact, the chromatic number of this graph really is 3. Okay, now there's no guarantee that this algorithm I outlined for you will give you the best possible coloring. Indeed, that might take some foresight or some backtracking, and it might end up being rather difficult to figure out, but it at least shows you a method that's not too bad that you could code if you have this information encoded into a computer to come up with a coloring that's kind of reasonable. And so this is basically what computer scientists would call a greedy algorithm. We're taking sort of one vertex at a time, we're never backtracking, and we're just choosing something that works. And we're doing it in at least a semi-intelligent way, where we're ascending from vertices of highest degree to vertices of lowest degree. But aside from that, we're just sort of letting things go as they may. Okay. So last up for today, I want to talk about something weird, which is going to be the chromatic number of the plane. Okay, what on earth is the chromatic number of the plane? Okay, well, first of all, I have to tell you what the plane is as a graph. So the graph here has as its vertex set all of R2. Okay, so far every graph we've talked about has had a finite vertex set. This has an infinite vertex set. Okay, so my vertices here are literally all the points in the plane. So it's, in fact, an uncountable vertex set if you want. And my edge set, this is the set of sets P1, P2. So these are just points in the plane, such that the distance between P1 and P2 is exactly equal to 1. Okay, so for example, if I pick as my points, let's say 0, 0, that's 1 point, that will be connected to the point 1, 0. It'll be connected to the point 0, 1. So these two will be connected. Sorry. These aren't connected. That was my point. Apologies. These aren't connected because the distance between these 2 points is the square root of 2. But if I did choose a point here where these things made a 60-degree angle, then I could make something where I have an equilateral triangle here. I'll let you use your trigonometry and figure out exactly what the coordinates of this point would be. And so those would be connected. And so I have this just gigantic graph that has in it all of the points in R2. And they're connected, again, if their distance between them is exactly 1. So note, this means the quote-unquote degree, by the way, of the origin, and indeed of every point, is definitely infinite. Because, for example, the origin is connected. Well, what are the points that are connected to the origin? Every point on the unit circle is connected to the origin because the unit circle is exactly the set of points that are distance 1 around it. And so indeed every point is connected to every point on the circle of radius 1 around it. Okay, quick aside just to make sure that we're on the same page. You might ask, is this graph planar? Okay, and so your first inclination might be to say, oh yes, definitely this graph is planar because the points in this graph are literally the points in the plane. So how much more in the plane could this graph get? Except, remember that being a planar graph means that you have to be able to draw these things without the edges crossing. Whereas if you tried to imagine all the edges that exist between these points, even just the points on the circle, it would be a humongous mess. There would be no possible way that you could get all of these things. And so, is this graph planar? Definitely not. If you really want to prove this, what you have to do is you have to find a subgraph of this graph that you know isn't planar. So if you could find a K33, for example, that would be one way to show that, hey, this graph is definitely not planar. But it is an open problem to ask, hey, what is the chromatic number of this graph? Okay. And in fact, it's an open problem that there's been recent progress on because we actually know a bound. Okay. So as of 3 years ago, what we knew was that 4 is a lower bound and 7 is an upper bound. But about 1.5 years ago, people actually discovered that actually this 4 you can improve. It's at least 5. And so what that means is that the number of colors that you need to color the graph of the plane is somewhere between 5 and 7. And so how do you prove something like this? Well, what you do is you explicitly produce a 7 coloring. That is, you show there's a function from R2 to 7 colors of your choice that meets this coloring property. Okay, so that's the first thing you have to do. And so that gives you this upper bound. And then on the other hand, you have to show somehow by finding a subgraph that the chromatic number is at least 5. That is, you want to dig up a graph in here that's complicated enough that you know somehow you can't possibly color it in fewer than 5 colors. Okay, so this is sort of an aside, but I think it's interesting because it connects this and just shows you how easy it is to come up with a problem that is relatively reasonable, but that no one knows how to solve. Yeah. So if you're bored and you want to advance the cause of mathematics while you're stuck at home, all you have to do is come up with a 6 coloring of the plane that meets this graphs, or meets this rule. So if you come up with a 6 coloring of the plane, then you will show that, in fact, this number is either 5 or 6, and then you'll be in good shape. All right, we'll wrap up there for this video. In the next video, we're going to talk about the interaction between planar graphs that we talked about last time and chromatic numbers. But until next time, be well.